All right, welcome back. So, I forgot to tell you guys on Monday, I'll always put the announcements on that side of the board and just leave them up there the whole class time. So our announcements for today are, one, you do have your online mastering homework due Friday by midnight. Most everybody's been able to successfully log on, and at least one person has completed the assignment. You can do pretty much the entire assignment with what you know now. There's nothing really tricky in it. So I would, if I were you, at least start it. Get a feel for the program. Don't wait till Friday. At all, yeah. Second thing, if you had, don't forget you have lab this week. We have the Toledo test. And the stuff is still for sale in the chemistry store. You don't need it next week, but you'll definitely need it the week after. So you can kind of budget out when to purchase it. And we'll have our group quiz on Friday. And it'll cover what we did Monday and what we do today. That's it. Questions on any of that? At the end of class, I'll just put up who the groups are so that you can kind of start to figure out who that is. All right, so last time we left on a cliffhanger. Let's see. I'm not. All right, can everybody see that? Is it big enough? Yeah. All right, so we left on a cliffhanger about states of matter. Hopefully, maybe some of you guys read ahead and figured out what the 3 states of matter are. If you haven't, 3 states of matter are solids, liquids, and gases. In fact, there's actually a 4th state of matter, but we're not ready for that yet. We're going to work up to the 4th state of matter. But for now, we'll just do 3, solid, liquids, and gases. So, right, matter is anything that has mass and occupies space, and so we can separate them into 3 broad categories. We can talk about solids, which have a fixed volume and a fixed shape. So our atoms are molecules. Are packed tightly together, which gives us a fixed shape. They're packed very tightly. We can talk about liquids, which have a fixed volume but an indefinite shape. Which is where our atoms and or molecules are able to move past each other. So they're packed tightly, but with some wiggle room. They can slide past each other. Then we have our gas, which has an indefinite shape and indefinite volume, which means our molecules or atoms they have lots of space between them. Bless you, bless you, bless you. Sneezy over there. So, gases have their molecules or atoms far spaced apart, lots and lots of space between them. So that is one way that we can classify matter, right? That's the visual way, right? It's a solid or it's a liquid or it's a gas. We can also classify states of matter based on what they're made of. So we can classify it by what's called composition. So when we classify something by composition, we are saying that we're going to start with a sample of matter. And does the composition vary if I take two samples from the same thing? So, for example, if I wanted to compare a glass of water versus a cup of chicken noodle soup. All right, so if I have a glass of water, or my water bottle, whatever, and I take a teaspoon or a tablespoon and scoop out 1 tablespoon, shake up the bottle, and take out another teaspoon, will those 2 teaspoons be identical? Right, because it's just water. Right, it's only one thing. Okay, so now you have your chicken noodle soup. You take 1 spoonful of chicken noodle soup, then you shake it all up, and you take another spoonful. If you haven't shaken your noodle soup, where are all the noodles? Right, they're mostly on the bottom. So if you take a spoonful off the top, what are you getting? Right, it's just the soupy part. But then if I shake it up, then I'm going to get a mixture of soup and noodles. So we can classify this as water is a pure substance where every sample is identical in a sample of water. Pure water, I'm not talking like ocean water or beach water or something like that, regular drinking water. Where a mixture means that, this would be my soup. The composition varies between samples. Now, within pure substance, there are 2 subcategories. You can have an elemental pure sample, which means that it is the pure element, right? So this would be oxygen gas, right? Just regular old oxygen off the periodic table in a gas, sample to sample, always just oxygen. Or we could have a compound, which would be like my water, right? It's made up of 2 different atoms, but water sample to water sample is always the same. Good so far? All right, mixtures. I can also subdivide those into 2 separate categories. So we can do heterogeneous and homogeneous. Which one means same all the way through? Right? Okay. So this is a mixture that is uniform throughout the cup, but between samples might be different. So let's go back to let's do a cup of coffee. So if I make my cup of coffee, right, I have the coffee in it, I have the milk in it, and quite a bit of sugar, right? The sugar ratio is pretty high in my cup of coffee. It's really almost coffee ice cream by the time I'm done with it. So, right, that is one way to make it. There's the other person who's going to have black coffee. Yeah, okay, the one person here drinks black coffee. So, technically, throughout the whole cup, it's all the same, right? So mine has a lot of stuff all mixed up in it. Black coffee has just coffee in it. So that is a homogeneous sample, but between my cup of coffee and your cup of coffee, they're different. That's not true if I had water. Like if I have water and you have water, it's just water. But a homogeneous mixture means that in my sample it's uniform and in your sample it's uniform, but our samples aren't the same. So however you want to explain that in words, I'll just say sugary delicious coffee versus black coffee. Heterogeneous is my chicken soup that was up here, right? So that a heterogeneous sample of my chicken noodle soup, right, the noodles are kind of at the bottom, the soup's at the top. Then you have a different combination of chicken, noodles, soups between someone else, so they kind of separate themselves out differently. Still a mixture, just means that there is a great difference in my sample and your sample, same thing. So, if that's all confusing, hopefully not too confusing, there's this amazing flow chart in your textbook. It is somewhere in the first chapter. It's probably like figure 1-1. So don't feel like you have to sketch it down. Just say figure 1. I think 1-1 or 1-2 out of the textbook. So here's all my types of matter. Does it vary between my sample and your sample? If the answer is no, then it's probably a pure substance. If the answer is, can I break it down into smaller bits? It's either an element or it's a compound. So here's my helium and my pure water. If it does have different compositions between different samples, it has to be a mixture. If it's uniform throughout all the samples, then it is either homogeneous, which is in this case a cup of tea with just sugar in it compared to another cup of tea with sugar in it, versus wet sand, where, right, if you've ever been, everyone's been to the beach. So you're at the beach, right, and you take your bucket full of sand, and like the water starts to come to the top, and the sand all goes down to the bottom. That would be a heterogeneous bucket full of sand. Yes?
So the heterogeneous, like it'll separate?
Mm-hmm.
Okay.
That's a good way to think about that. It does physically separate. You can kind of see layers in it. All right, so now we have our states of matter all kind of sorted out. We can talk about how to change matter from one form to another. So, you are always experiencing chemistry, right? You have water evaporating, you have your metal rusting, you have your wood rotting, you have your ice cubes freezing, all chemistry. But what happens during these changes? This is going to be my very scientific answer. Depends on the type of change. That's not a good sentence. There are two types of matter. There are two types of changes matter can undergo. That's actually what I wanted to say. There are two types of changes. Same would happen in the other two types of changes? Once there's a P, once there's a C? Chemical and physical. Mm-hmm. All right, so obviously we're now going to talk about what the difference is between a chemical and physical change. So let's talk about definitions. A physical change does not alter the composition or the identity of the substance. Oh, that got worse. Try that again. There we go. Where a chemical change alters either the composition or the identity of the compound. All right, so let's talk about some physical changes. So, In a physical change, I haven't changed the compound I'm talking about. So if I'm looking at water, I go from water to ice. Is ice still water? What has happened to my water? Right, it's frozen. So a physical change could be something like freezing. What if I go water to steam? Is steam and water the same thing? Right, it's the same compound, but what have I done to my water? Right, I boiled it or heated it. So these guys are physical changes. Right, freezing, boiling, sublimation. I make my box big enough. Just something where I change the state of matter. So a physical change right, so from water to ice, I went from a liquid to a solid. Water to steam, I went liquid to gas. Sublimation, now it goes solid to gas. So I haven't changed what it is, I just changed what state it's in. Let's talk about chemical change. Chemical change is where atoms rearrange themselves into a new substance. So let's say I have, oh, this is good. Let's say I have a sample of wood, a log, I guess I have a log, and it is chilly outside and I decide to have a campfire. So I start off with a log and then I light it on fire. At the end of my campfire, do I still have a log I can build a building with? No, what have I done to it? I burned it, right? I turned it into charcoal. Can I undo that? Can I push my charcoal bits together back to make a nice, no. Okay. So burning is a chemical change because I can't undo it. That's a good way to think about it. Let's say you have a super nice piece of metal, but you forget it outside for about 6 years. It's probably not that important to you if you forget it outside that long. What will probably have happened to that super nice piece of shiny metal? It'll be all rusted. Can you ever put the holes back together and make it look as nice as it was? No. Maybe you can put some Bondo on it and then like a primer, and then sand it down and maybe paint over it, but you still can't fill the hole. Okay, so that would be rusting. Right, it is a chemical change that cannot be undone. So you've turned it into something else. Does that make sense? A physical change, I can undo it, right? So I went from water to ice. I can undo that. I can go from ice back to water. Or I can go water to steam. I can undo that. I can go back to water. I can't unburn the wood, and I can't unrust the stuff. Good. And again, another snazzy picture from your textbook. This should be still in chapter 1. I think it's like 1.4, It just says different changes things go under. So, let's talk about another important science chemistry thing, which is measurements. So, in 1999, you guys were like, what, 3, 4? Probably don't remember this particularly well. But the Mars Climate Orbiter was launched to go land on Mars. This is like the predecessor of the Mars rover. This was the first shot at the Mars rover. So they shot this rocket, they sent it to Mars. And they realized once the satellite got up there, they're like, man, we're having some difficulties getting it to go where we want it to go. Turns out the Americans chose to use English units, so feet and inches, and the British folks decided to use metric. And so half their measurements were in one set of units and half were in the other set of units. And the satellite, super confused, and was lost in space. And so that was probably like a $20 million project, lost, because they forgot to check their units. Same thing can happen on here in a smaller version. So everything we do in here has units. Your grade can definitely be lost if you're not paying attention to your units. So from here on out, we are going to be unit crazy, loving our units, making sure we're in the right ones. So let's talk about, I'm kidding, it was a $125 million satellite. Way more expensive than I thought, $125 million. Lost forever. Somebody will find it and be like, what is this thing? All right, so point is, units are going to be super critical. Which unit do you think we're going to use in here, metric or English? Metric. In here, all the time, always metric. So from here on out, we're going to be thinking in metric units. So if you don't have the units off the top of your head, table 1, 2 in your textbook is where you can find them. The ones in bold will be the ones we use most often. So you'll need to be able to know that kilo, if it's 10 to the third, what do we normally call that number? 1,000, right? So 1,000 is a kilo. 0.01 is a centi. 0.001 is a milli. And this guy down here, there, 1, 2, 3, 4, 5, 6, 7, 8. Nano. Those are going to be the 4 units we really need to be able to convert between. So if you don't have those off the top of your head, make a little star. Go back and learn table 1, 2. So let's talk about what are some of the scientific units we use. Oh, same thing. Table 1, 3, you will not have to memorize conversion factors. I will give you all the conversion factors, but you'll probably need this table to do some of your homework. Because I know for sure some of the homework says, if I have 90 feet, how many yards do I have? If I have 80 yards, how many meters do I have? Things like that. So this table 1, 3 will be useful to refer to. All right, so let's talk about units of measurements in science. So length. I put way too much space in all these slides. I only have like one sentence for each of these, so sorry if I made you waste paper. I think every year, oh, I should probably condense it, and then I forget. All right, so meter has the abbreviation little m. A meter is 39 and a little over 1/3 inches. The most common meter, well, the common units. Are going to be these guys. I guess the kilometer. Right, so we have our meter. We have our centimeter. We have our millimeter. We have our nanometer. And our kilometer. right, so if you're thinking about how big everything is, this, right, this guy's the meter stick. Do it this way. So this guy's the meter stick. A centimeter is, right, this much of the, so meter, yeah, is this much of the meter, this little bit here. The millimeter is this tiny little bit of the stick. The nanometer is the width of your hair. So if you can look at one piece of hair and you measure across, that's about a nanometer. And a kilometer is 1,000 of these sticks, end to end to end to end to end. Okay? Then we can also talk about mass. Mass is typically measured in kilograms, or, let's see, so kilograms or kgs. It is more common for us to measure mass in grams, which is a little g. And if you're thinking between them, it takes 453 grams to make up a pound. So a gram is much, much, much less than a pound. Woo. All right, so kilograms, grams, and then, right, we could do milligrams or nanograms also. Those would be the ones we go between. All right, let's talk about time. Our standard unit of time measurement is going to be seconds. All right, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. I could write that down. Everyone feel pretty confident about that? Okay, we'll move over to temperature then. I don't want to assume that everybody knows time measurements. All right, so temperature is a measure of motion. In general, hot molecules are going to be moving fast, cold molecules are going to be moving slow. If you're thinking, man, why is that? Don't worry. We're going to cover that this semester in the kinetic molecular theory of gases. Spoiler alert, tells you that hot things move fast and cold things move slow. But we'll talk about why later. So if hot molecules are moving fast, and temperature then is a measure of this motion, where hotter things are moving faster, colder things slower. There are two temperature units we'll mostly use in here. We're going to talk about Celsius and Kelvin. Leave that Fahrenheit junk at home. We're going to be talking about Celsius and Kelvins. So Kelvin is the absolute scale. That's the one we're going to be using most of the time. Kelvin is designed so that 0 degrees Kelvin is no motion. It means there is no molecule with any energy to go anywhere. So 0 Kelvin, sometimes called absolute zero. The idea is that there is no energy for those molecules to move around. They have completely stopped. Celsius is a more common temperature measurement, and it is where 0 degrees Kelvin is where water freezes. So that's what they considered 0. 0 on the Celsius scale, water freezes. 0 on the Kelvin scale, everything's frozen. And then to convert between the two, Let's see, what's the best way to write this? Convert Kelvin to Celsius. Add 273 to the degrees Kelvin. So 0 degrees Celsius is 273 Kelvin. Weird little thing, Kelvin doesn't get a little superscript O. Whenever they developed Kelvin, they decided to leave that off. It's not a big deal one way or the other, but technically, no, whatever that is. I don't know if it's an O or a 0. I wasn't part of the conversation when they developed it, so I would have set them straight. Questions about any of this? All right, let's talk about volume, density, and then we'll wrap up with some calculations, moving some basic math. All right, so let's talk about volume. Volume is a measurement of space and cubic length. Right, length cubed, cubic length. All right, so our units of volume are usually liters, which gets a capital L. And milliliters, little m, big L. Those will be the two units we most often use. And so if it's length cubed, right, we had our length units a few minutes ago. So if I have 1 centimeter cubed, that is equivalent to 1 milliliter. So if I have a centimeter box, that is 1 milliliter. If I have 1 meter cubed, that's 1,000 liters. Good there. All right, in that case, let's talk about some density, which is relating masses, like grams, into, and volumes, like liters and milliliters. Has most people seen that equation before? Density is mass divided by volume. Most of our densities are going to be measured in grams per milliliter. So our mass will be in grams and our volume will be in milliliters. So let's shake it out and find your calculator if you brought one with you. And we'll do some very, very basic math. We're going to do division. Hope everybody's ready for that. If you didn't bring your calculator today, that's all right. I know you'll bring it next time. Because from here on out, we're going to be doing some calculations just about every day. I'm actually going to flip over the page and write down my question. So I found a shiny piece of metal. I'm hoping it's platinum. And I become rich, and I can retire to an island. I know by looking it up, platinum has a density of 2.15 grams per milliliter. What I have has a mass of 50 grams and a volume of 4.49 cubic centimeters. Can I retire based on that? So, I had to figure out, right, the density of my unknown. So, density is mass divided by volume. So which one of the three numbers in the problem is the correct mass to use? The 50, okay. And then which of the remaining numbers do I put on the bottom? Okay. Is it okay that's in cubic centimeters? It is, because right, it's the same as milliliters. All right, so double checking on my calculator. 50 divided by 4.49. Yep. Not retiring. Probably just a piece of junk. How do you feel about that? Good warm up? Yeah, everybody figured out where the division button was on the calculator? Excellent, we'll be using that a lot. How do you feel about density? Okay. All right, in that case, let's talk about how we measure things and the reliability of a measurement. All right, so let's say I have some water and I want to measure out 50 milliliters of water. Then I'm going to measure it again with my beaker. All right, you ready for some amazing artistic drawing? Okay, hopefully yours looks as good as mine. All right, there's my beaker. Well, not my worst beaker. See, it's in 3 dimensions. So if I have my lines on my beaker, 1, 2, 3, 4, 5. Right, so it's like every 10 mils to hold up to 50. Or I have my fancy graduated cylinder. If anybody wants to learn how to sketch as amazing as this, I'll be giving lessons later. I don't have enough lines in here. Imagine there's 50 lines in here, and they're more evenly spaced than I drew them. All right, so I have a line every 10 milliliters, so I have a line every 1 milliliters. So, looking at my beaker, if I want to fill it up to the 50 line, how accurately can I land exactly on the 50 line? Not very, right? Technically, it's going to be 50 plus or minus 10 mils, because I'm either going to be below it or I'm going to be above it. So it's 50 plus or minus 10 mils. Over here, I can be at 50 plus or minus 1 milliliter, all right? Because either I'm just below it on the line down at 49, maybe I overshot, I'm at 51, but I know for sure which side of it I'm on. So when we talk about measurements, we have to talk about the fact that every digit is certain, except for the very last digit at the end. And this digit's an estimate of what you actually measured. That's not spelled right. So we're going to use this method called significant figures. How many people have done significant figures? How many feel confident in their significant figures? Okay, good. So significant figures is how we're going to tell the readers which digits are accurate and which ones are estimates. So in this method of significant figures, every measurement, right, can't be 100% certain. So every measurement is going to have a little bit of uncertainty. And these measurements have to tell the other reader which ones are accurate and which ones are not accurate. And so we do this by the number of zeros after the decimal point, or remove the scientific notation to try and get around this. So significant figures, we talk about the number of meaningful digits. So if I look at this measurement, 8.00, there's a total of 3 significant figures. If I talk about 8.0, there's 2. If I talk about 8, it's 1 significant figure. So the precision of a measurement depends on the method of measurement and does affect the final calculation of whatever you're measuring out, right? So if I use the beaker, give or take 10 mils, I'm using the graduate cylinder and plus or minus 1 mil. So the bigger the uncertainty, the more it affects subsequent measurements. So I am not going to spend time doing significant figures in class because that's what your lab is next week. You're going to do a significant figures worksheet. There is a similar worksheet on my class website if you want to go ahead and kind of get started. Like there's significant figure rules and practice problems and whatnot if you want to go get them. Let's see what I have left. Yeah, we can do this. We'll do scientific notation as our last thing. Oh, question first.
Sorry, the significant figures, is that for the lab tomorrow or next? Sorry, so
Next week.
Okay.
Yeah, so next week, the lab is doing a significant figure worksheet.
Okay.
So we'll do one last thing. We'll talk about significant or scientific notation. Again, a topic that probably most people are familiar with, right? Scientific notation, mostly. So if I'm looking at the number of atoms in 12 grams of carbon, it's really big. It's a lot of zeros. So we usually write it, bless you, where we have all the digits and then times 10 to the number of zeros. That's the easier way to write that. Or sometimes something is very, very, very small. So we write that the same way. We write all the digits multiplied by 10 times the number of zeros. So the negative sign tells me it's a less than 1. Positive tells me it's a greater than 1 number. So we'll do some quick practice, then I'll let you guys go. So let's convert the following to scientific notation. So I'll start us off. What do I do with those other 2 digits? 2 options. I could do 3.27, that's fine. All right, is this going to be a 10 to a negative something or 10 to a positive something? Negative. Okay, then how many negatives do I need to put in there? 10. Okay, let's do the other one. Oh, I do, thank you, units. So what do I do with this distance? 1 and then what? Okay. 0.5 will be a positive or a negative exponent? Positive, and let's see, it should be 3, 6, 7, 8. Is that right? Everyone feeling confident about that? Good. All right, so the only thing left for today is I figured